I guess you have figured out by now that there is always a quiz at the beginning of a video, so here it is. So a quick recap. We saw nodes generate data and links carry signals in the form of electromagnetic waves. So what's the next task? Basically convert data into signals. So this process is called encoding or modulation. We are not yet covering this in this video. We need to do some theory first. Suppose someone were to give you a physical link to transfer the data. What are the things you will be interested to know about this physical media? I, for one, would be interested in these three things. One is data rate. So basically, I would like to know how many bits per second I can transfer on this link. So this data rate is typically expressed as bits per second, kilobits per second, megabits per second, or gigabits per second. The second question I'll be interested in is what is the probability of a packet error on this link? Packet is nothing but made up of bits. So if I were to send this packet consisting of bits on the link, what are the chances that some of the bits in this packet will be in error? The third thing I'll be interested in is if I were to send bits, how long will they take to reach the receiver? So that's the delay. This is also something I'll be interested in. So in this video, we will answer these three questions. Probably if it were someone like my parents, the first question they will ask is how much does this link cost per foot? That's not something we will bother about. Let's start out with a simple question. Suppose you were given this data and asked to convey this data to your friend who is far away, and there is a wire pair that is connecting you and your friend. Now, how will you convey this data? Now, I don't want to hear this. So think about it. You may have some other interesting way, but a simple method is to represent the bits by voltage levels. For example, 1 is represented by the positive voltage level X volts and 0 is represented by a negative voltage level minus X volts. This type of encoding, that is converting bits into voltage levels, is called non-return to zero encoding, that stands for NRZ. Before we answer the three questions we asked earlier, it is useful to understand the waveform that is being sent on the physical media. So this brings us to Fourier analysis. So Fourier analysis shows that any signal can be decomposed to sinusoids of different amplitude, frequency and phases. Didn't understand that? Let's look at this example. Suppose you have this particular waveform. This is nothing but bits, ones and zero going on till infinity. So if you have this waveform, which is periodic in this case, Fourier analysis shows that this waveform can be represented in this particular fashion. Basically, it is a summation of these sinusoids of different amplitudes, because there is this term k, and in this case it turns out k is odd, as well as different frequencies because you are multiplying f with k. By the way, this f is nothing but 1 over t, where t is the periodicity. The phases in this particular example turn out to be the same, that is equal to 0, but some other waveform can have different phases for different components. So this is the time domain representation of the signal. Often it is useful to look at the signal in the frequency domain as well. What do I mean by the frequency domain? Basically, it lists the frequency components that are present in this particular signal. If you see here, since k is odd, the frequency components, the sign terms that are present correspond to f, 3f, 5f, 7f, so on. So that is what is being represented here. So you have terms only at the odd frequencies. So this frequency domain representation also captures the strength of the frequencies. As you can see, the strength is a function of 1 over k, whereby as the frequencies increase, the strength is progressively decreasing. So this is the frequency domain representation of this square waveform. By the way, I have only plotted up to 29f, but this actually goes on till infinity as shown here. Now this figure shows how those sine terms make up the square wave. So if you just look at the sinusoid, so this is just the first frequency component, which is 2 pi ft. So this is the sinusoidal waveform. It is nowhere close to the square waveform. Now if you add the second frequency component, which in this case turns out to be 3ft, so this is the summation of two frequency components f and 3f, you get a waveform like this. And when you add three frequency components f, 3f and 5f, it starts to look like this. And as you add 4, in this case f, 3f, 5f, 7f, it starts to resemble the square wave more and more closely. As you keep on adding, it becomes a square wave. By the way, this frequency f and other frequencies are multiple of this. This frequency f is called a fundamental frequency. And this is a function of the periodicity, which is 1 over t. What we have seen earlier is a periodic square wave. What we have here is a pulse. This aperiodic pulse is of duration tau, so this is tau, and this is the frequency domain representation of this particular pulse. Now tell me, what is the difference you observe between this frequency domain representation of this aperiodic pulse versus the frequency domain representation of the periodic square wave? Right? In the earlier case, the frequency domain representation was discrete, whereas in this case, it is continuous. The earlier discrete representation is called Fourier series representation, whereas this continuous representation is called Fourier transform. We won't get into any more details other than this. Now going back to our original NRZ signal, which is shown here. Now what do you think this signal is, periodic or aperiodic? Well, there is no periodicity here. This is a random bits. This is the frequency domain representation of this NRZ signal. I'm calling it random because in a generic case, the ones and the zeros are chosen with equal probability of half. We are going to define two terms in this context. One is the spectrum of a signal, another is the bandwidth. So the spectrum of a signal is nothing but the range of frequencies it contains. So this signal contains all these frequencies. In fact, these frequencies go all the way till infinity. Now the bandwidth is nothing but the width of the spectrum, that is all the frequency components that are present as part of this particular signal. Now what is the bandwidth of this random NRZ signal? Now don't look at this and answer 1 over t. Simple, the absolute bandwidth of an NRZ signal is infinity because it has frequency components ranging all the way till infinity. One thing to notice here is that the energy of the signal is concentrated more in this band, roughly let's say until here, and it progressively decreases as the frequencies increase. So what this means is if some of these higher frequency components are eliminated, you can still recover the signal. The signal is no doubt distorted, but still you should be able to recover it. So instead of absolute bandwidth, which can often be infinity for these aperiodic signals, what is often used is called effective bandwidth. The bandwidth that helps recover the signal. For this NRZ signal, what is often used is this first null bandwidth, basically the position at which you hit the null, which is where the strength falls off to 0, that is equal to 1 over t. So that is the first null bandwidth. For this NRZ signal, what is this 1 over t? This is nothing but the data rate of the NRZ signal, because as you can see here, each bit is of duration t, that is you are sending one bit every t seconds. Let's spend a little bit more about understanding the bandwidth of signals. Suppose I took an NRZ signal with an absolute bandwidth of infinity and I were to pass it over a link which has finite bandwidth. We talked about link bandwidths earlier. The question that is interesting here is how much link bandwidth do I need to provide to recover the signal properly? So here is an NRZ signal with an absolute bandwidth of infinity. The bit duration is t. In this particular case, let's say we set the bit rate to 2000 bits per second. So here is a spectrum of this NRZ signal. So the first null bandwidth is 1 over t. For this particular case, how much does this correspond to? 2000 Hertz, right? Because this is equal to the data rate. Now suppose I were to pass this signal over a link with bandwidth of only 800 Hertz. So this is the link bandwidth. What this basically means is I'm going to pass these components. Let's assume this is 800 Hertz. All these other components I'm just going to eliminate, because the link will not pass those other frequency components. Then the received signal will look something like this. As you can see, you can make mistakes here because even here there is some positive voltage level where you could interpret a 0 as 1. Now if you were to pass it through a link with bandwidth 1000 Hertz, this is how the signal is going to look. Now as you can see, as you increase the link bandwidth, you are now going to get a waveform that resembles the transmitted waveform closer and closer. So the interesting question here is, what is the minimum bandwidth that I need to provide so that I can recover this sent waveform without any errors?